Welcome to our discussion on a family of functions. There are really six big families of functions, groups of functions, functions that have similar properties, similar graphs, those types of things. We have the simplest, the linear function. We have the polynomial functions. Power functions, those are just things that are raised to a power like x squared, x cubed, things like that. There's rational functions, which are functions that have variables in the bottom of a fraction. There are the trigonometric functions, sine, cosine, tangent, etc. And then there's exponential and logarithmic functions. You can think of those as two different families, but since one is really just the inverse of the other, they really are lumped together. Okay, why do we bother with this? Because we want to be able to model things that are happening in the real world. And a mathematical model, usually using a function, is something that we use in order to be able to make predictions. So we have some real world problem that we want to describe, predict, work with. So we formulate some sort of mathematical model. We test it, see if it works, right? We solve that model, we make some conclusions, and then we can make some interpretations as to what might happen with other values and later in time and things like that. Please be aware that models are never perfect. They're always a generalized idea. Even if they fit your data perfectly, we don't know if they're going to fit future data or data outside of our scope of sample. So it's always, living in kind of an ideal bubble, and it's the best that we can do in that bubble. All right, let's look more closely at some of these. A linear function or a linear model, you guys are familiar with these. It's just anything that can be modeled by a straight line. Our friend y equals mx plus b, but instead of y equals mx plus b, now all of a sudden we're just going to write it as f of x equals mx plus b, because now we're talking about a linear function rather than just a line. Typical example, y equals 3x minus 2, slope of 3, intercept of negative 2. We can plug in a bunch of x values, get a bunch of f of x or y values, and then this is supposed to model something. In this particular case, this is modeling something with a positive growth, right? Because the slope is 3. And in fact, that tells us that whenever the x value goes up by 1, the f of x or y value goes up by 3. And that's really what a slope is. It tells you how fast or slow something is increasing or decreasing if it's a negative slope. Here's a simple example. As dry air moves upward, it expands and cools. If the ground temperature is 20 degrees Celsius and the temperature at a height of 1 kilometer is 10 degrees Celsius, we can express the temperature, capital T, in degrees Celsius as a function of height h in kilometers, assuming, of course, that this is a linear relationship. We only have 2 points, so for all we know, those 2 points could be on any kind of function. We're just going to assume that it's a linear function. So you can work through this on this slide. Basically what we're doing is we're taking this information and we're taking those 2 bits of information and thinking of them as ordered pairs. If they tell us the ground temperature is 20 degrees Celsius, then that means our height is 0 and our temperature was 20, because remember our height, right, is the x. And then the second piece tells us that if we're at a height of 1, our temperature is 10. So now if we want to come up with our function, right, which we can think of f of x instead of y, well, if you're given 2 points, how do you find a straight line? Well, step 1 is find slope, right? Change in y over change in x. So how about 20 minus 10 over 0 minus 1, 10 over minus 1, or negative 10. And now I have slope. Take either one of my points and I can plug it into the point slope form. The y minus y1 equals m times x minus x1. I'm going to choose this point because it's the easiest. because now it's y minus 20 equals negative 10 times x minus 0. Y minus 20 equals negative 10x. Y equals negative 10x plus 20. Well, you should have kind of already known that b was 20 from this point right here, right? Because b is your intercept. That's what we're doing here in this slide. We're just doing it with h's and t's, right? We had from our previous slide that y was equal to negative 10x plus 20, but this function is supposed to be a function of temperature with respect to height. So that's why we write it in terms of h. There it is graphed. Obviously, you always have to take into account what things are logical. If h is height, then this thing cannot be defined for negative h's, because you can't be at a negative height. I mean, technically you could be below sea level, but that doesn't really work when we're talking about air temperature. Also, as we're graphing the function and we're getting these temperatures, these t's, at some point it's going to get too negative to really be realistic. So there's also going to be a cutoff in that sense. Also, it gets to the point of how big can your height actually get before you are out of the atmosphere, and then you're out into space, and then different rules apply and all that kind of stuff. If we want to figure out what the temperature was at a certain height, it's just a matter of plugging that into our function that we've now found and solving. Very simple. Okay. Just remember, as we've kind of talked about, that this is all our best guess. Okay. If there's nothing given to you to kind of provide you some guidance as to what you're supposed to do, then you're just going to find a curve that fits the data best. In this case, we only had 2 points, so really we could have guessed anything. Alright, polynomials. You guys have seen polynomials before. They're just a bunch of different powers of a variable added and subtracted together. In this case, x. It's almost always x, but it doesn't have to be. Alright, so here's a simple, typical version of a polynomial. A polynomial of degree 1 is a straight line, because then x just has the power of 1. And then degree 2 is our quadratic, which we use a lot. And then everything after that, we just kind of lump them in with all the general polynomials. Here are a couple different versions that we've seen before. If the leading coefficient is positive, we know that we're going to get an opening up, and if the leading coefficient is negative, we're going to get an opening down. When we're dealing with quadratics, the rules are different for other powers. We know that if we have a degree 3, we have something that looks basically like a lightning bolt, right? Kind of looks like a lightning bolt. And then degree 4 will always be more or less like a quadratic. So all of your even powers are going to be like a quadratic, and then all of your odd powers are going to be something like this or something like that. All right, depending on if their leading coefficient is positive or negative. So with this one here, even without looking at the answer down there, you know that it has to be an odd function, because you get a negative infinity in one direction and positive in the other. Okay, how about an example if we drop a ball from some sort of height, in this case the deck of the CN Tower, 450 meters above the ground, and then we model its height above the ground every 1 second as it drops. We put those numbers into a table, and then we try and figure out a way to model that height. If we graph those numbers, we look at that and go, well, it kind of looks a little straight, but then there's that curve at the top. So instead of trying to fit a straight line to it, you end up fitting a quadratic to it. And it just so happens that this ends up being the best fit. And when you plot that line on the dots, you can see that it's in fact a very good fit. It hits those dots pretty perfectly. So the height of an object, acting under the force of gravity is always going to be modeled very, very effectively by a quadratic, which is one of the reasons why we spend so much time dealing with quadratics, because we use them so often in physics. We can, of course, always use the quadratic formula to solve and figure out when the height is 0. Power functions are they're kind of a special version of polynomial functions, because instead of having multiple pieces, it's just the first piece, right? It's just x to a power. So it's kind of like a really simple version of a polynomial function. And as we said before, if the power is 1, we get a straight line. If the power is 2, we get a normal parabola quadratic. If the power is 3, we get that kind of lightning bolt shape. Power 4 goes back to looking like a quadratic. Power 5 goes back to looking like a lightning bolt. So every time it's an even power, it looks like the horseshoe, right? It looks like a quadratic. And every time it's an odd power, it looks something like the lightning bolt. And that's what it's talking about here. We can also see that they have certain similarities, i.e. they always go through the point 1, 1 and negative 1, 1 if it's an even power, and then 1, 1 and negative 1, negative 1 if it's an odd power. And then all that happens is the shape is slightly different depending on those powers. Okay, another version of the power function is 1 over, because if you 1 over n being the power, right? So a root is also a power. The square root is something raised to the 1/2 power. The cube root is something raised to the 1/3 power. So we can lump those in with the power functions, even though their graphs are going to look drastically different. If you have a root power where the root is odd, you're going to get basically the sideways lightning bolt. If you have an even root power, 1/2, 1/4, things like that, you get a sideways parabola, but you only get half of it, because if you had both halves, it would no longer be a function, right? If we had that true sideways parabola, you would have that other piece down here, and then it would fail the vertical line test. So you really, that's, the graphs are very similar. They've just been rotated. How about if we actually have the power of just negative 1? So then we get just 1 over x. Then we get this kind of special hyperbola. Here's an example of something that is hyperbolic in nature. Boyle's law. When a temperature is constant, the volume V of a gas is inversely proportional to the pressure P, and you can see C is a constant. The constant is based on the type of gas you're dealing with. So P is the thing that varies, right? In inversely proportional to the pressure P. So P can vary. That's like your X. So this is really just a special version of 1 over X. Only now it's 1 over P, and then times some constant, so you get C over P. Okay? Now when this is the case with Boyle's law, we only get the right-hand half of the hyperbola. Remember, this had at both pieces, and the reason why is because, remember, our input, look at our picture, right? The input variable is P, so we're giving it a pressure, it's giving us a volume. You can't have a negative pressure, right? So these models, even though algebraically we have the negative half, these models are supposed to model things in the real world, so you always have to take into account that sometimes, even though the function itself might have a very large domain, the model might have a very small one, because you have to limit it based on real world situations. Okay, rational functions. Anytime you have a function in the bottom of a fraction, and a function meaning just something in terms of a variable. So basically, anytime you have variables in the bottom of a fraction, you have a rational function. So in fact, the previous one that we just looked at was a version of a rational function, because 1 over x, right? The top polynomial, the p of x, is just the constant polynomial 1, and then the bottom is just the simple linear polynomial of x. Anytime you're dealing with rational functions, these are one of the two that you always have to worry about your domain. Right? You're going to have domain issues with these, because this can never be 0. So your domain is going to be everything except for those things that make the bottom function equal to 0. The other domain issues we have are these, right? Cube roots are fine. Any odd powered root is fine. These are okay. But the even powered ones, those are the problems, as we saw here, right? So anytime you have an even powered root, that's where you have to worry about your domain. Okay, so for n equals 2, or really for any even root, you have to worry about your domain. You have to restrict it so that you're not taking an even root of a negative number. Here's another version of a rational function. Right? You can see that it's just some sort of function of x over some other function of x. And then to graph it, the first thing you always have to do is set the bottom equal to 0 and solve. And this ends up being x plus 2 times x minus 2 equals 0, and this of course gives you a 0 at negative 2 and positive 2, and there are your two vertical asymptotes, and then you go on from there. An algebraic function is really just any function that you can make from combinations of the kind of small families, right? So any combination of a polynomial function and a power function, or a rational function and a polynomial, etc., etc. Those are just, we call them the general algebraic functions. In fact, if you had, slap some trig in there, and you could still call it an algebraic function. It's just kind of a general term. Here are some versions. Here's another version that deals with the theory of relativity. Trigonometric functions, you guys are all familiar with these: sine, cosine, tangent, cosine, cotangent, and cosecant. The graph of sine and cosine, you should be relatively familiar with these. It's helpful. You should be relatively familiar with knowing that the output of sine and cosine is always between plus and minus 1, right? The standard function has a maximum height of 1 and a minimum of negative 1. You should also know the zeros of these functions. So when is sine of x equal to 0, and when is cosine of x equal to 0? Same thing with tangent. You should know its general graph. You should know where it's undefined, right? So where all those vertical asymptotes are, and then where does it equal 0. Those are kind of the biggies. We want to know when functions equal to 0. We want to know their minimums and maximums, and any points of discontinuity. The period of all these functions is good to know. Sine and cosine repeat every 2 pi, and then tangent repeats every pi. Alright, exponentials and logs. First we'll look at exponentials. Exponentials are they're like a power function, only before, with a normal power function, right? A power function was x raised to some constant. Here, an exponential function is some number, some constant we'll call a, raised to x. Totally different, right? It's still something being raised to a power, but in this case, x is the power. Now if your base, a is the base, right? Base a. So when we talk about the base, we're talking about this number here. When your base is bigger than 1, you get this looking function, and when your base is between 0 and 1, so a fraction, it flips. It seems to flip over the y-axis. These functions, no matter what your base is, they always have similar properties. The range is always from 0 to infinity, and it's always a round bracket because it never actually equals 0. It just gets asymptotically close. And the domain is always all numbers. It goes as far to the left as you want and as far to the right as you want. Exponential functions show up a lot in the real world, in the natural world. Natural phenomena such as population growth, whether it's people, caribou, bacteria in a petri dish, those things grow exponentially. Money, we use it a lot. Exponential growth is used for compound interest, continuous compound interest. And then also radioactive decay is a version of exponential growth where the base is less than 1, because remember, if the base is less than 1, things get smaller as you go out in time. Logarithmic functions are really just the inverses of exponential functions, but they do have very specific uses. We see logarithmic functions to model earthquake scales. We also use logarithmic functions to do the pH scale and other things in chemistry. So it's going to be important for you in various careers or classes to understand log functions. You need to know that they are the inverse of the exponential function, which is why it looks like they've been rotated 90 degrees. And so everything has been changed. With the exponential function, right, a to the x, our domain was everything, and our range was 0 to infinity. Since log functions are the inverses, then log base a of x, they trade places. The domain is now 0 to infinity, and the range is now negative infinity to infinity. That's what happens when you have inverses. Before the exponential function, it went through the point 0, 1, right? That point was, all of them went through that. This one, these all go through the point 1, 0, right? They've switched places because they're inverses. Last but not least, we can kind of test our skills now that we've seen all these. Can you classify each of these into one of the families? So pause the video, take a second, make sure you can recognize what kind of functions all of these are. And here are your solutions. 5 to the x is an exponential, x to the 5 is a power function. The second one is an algebraic function, or you could have said rational function would have been fine as well. And then the last one is a polynomial function, algebraic as well. I mean, they're all algebraic because that's a general term. All right, that's everything you need to know about families of functions.